Hi, I'm Emily Allen, and this is my Unit 2 Case Connections video. So I chose to do Case 1 and Case 4. So starting off with Case 1, it is asking about the pyruvate kinase enzyme. And it starts off by asking, under normal conditions, describe all the ways in which pyruvate kinase is regulated in the cell. So I made this little diagram. Pyruvate kinase catalyzes the step in glycolysis where phosphoenol pyruvate is converted to pyruvate. Pyruvate kinase is inhibited by ATP, acetyl-CoA, glucagon, and long-chain fatty acyl-CoA. So starting with ATP, it inhibits pyruvate kinase because when you have a lot of ATP, your body has a lot of energy. ATP is a product down the line from glycolysis. So when you have a lot of ATP, you do not need glycolysis to proceed as quickly. So hence it inhibits pyruvate kinase, thus prohibiting the conversion to pyruvate and the creation of more ATP down the line. Acetyl-CoA is kind of the same reasoning. After pyruvate is created, it can be converted to acetyl-CoA. So when you have a lot of acetyl-CoA, you don't need that to happen, so you don't need pyruvate to be created. To explain glucagon, I'll first explain insulin. Insulin is a positive regulator of pyruvate kinase. So when your glucose is high, insulin is high. So you want glycolysis to occur to break down this glucose. So insulin upregulates pyruvate kinase to make glycolysis happen more quickly. Glucagon does exactly the opposite. So it wants to slow down glycolysis because you don't need the breakdown of glucose. So glucagon actually inhibits this enzyme by phosphorylating it. Long-chain fatty acyl-CoA is also a product down the line of glycolysis, so you do not need glycolysis to occur because you have enough of this product, so it inhibits pyruvate kinase. Insulin, like I said, wants to promote glycolysis, so it wants to promote the pyruvate kinase enzyme. It does this by dephosphorylating the enzyme and making it active. The phosphorylated version of this enzyme is an inactive form, so by dephosphorylating it, insulin activates it. And then fructose 1,6-bisphosphate positively regulates this enzyme through a feed-forward reaction. Fructose 1,6-bisphosphate is a product earlier in glycolysis, so in an earlier step. So basically, fructose 1,6-bisphosphate comes and acts on pyruvate kinase and basically tells it that there's going to be a lot of this product coming down the line, which means that there's going to be a lot of phosphoenol pyruvate that needs to be converted to pyruvate. So it upregulates the cell in turn. The other thing that this case was asking about is the M2 isoform. So pyruvate kinase has different isoforms, and some of these are the M2 isoform and the M1. So it says that the isoform M2 is characteristically found in a low activity state and is ineffective at promoting glycolysis. And it asks that this logic seems counterintuitive for a glycolytic tissue. What is the rationale for this mechanism, and what other pathways may cancer cells be diverting to? So it also says that cancer cells have been shown to prefer type M2 over type M1, which is counterintuitive because you would think that cancer cells would want the glycolytic type M1 cells. So I said that though the M2 isoform is in a lower activity state and does not promote glycolysis. The lower energy state actually allows it to form glycolytic intermediates, which can be used in other pathways that synthesize lipids, amino acids, and nucleotides. I have an article in my reference page that states that the M2 isoform also acts as a stabilizer for cells and helps in the transcription of genes. So even though the M2 isoform is not helpful in glycolysis necessarily, it is helpful to cancer cells in other ways, which makes it plausible that this form is expressed over the M1 glycolytic form. So then moving on to case 4, this case presents a previously healthy 2-month-old that's been jittery after breastfeeding. Her mother says that she hasn't given the baby anything to eat other than breast milk. The baby has been sleeping for long periods between feedings, and the symptoms started when she started noticing the sleeping for extended periods of time. Lab results showed low blood glucose, and when epinephrine was administered, there was no increase in blood glucose, but there was an increase in blood lactate. A physical exam showed an enlarged liver, and it also notes that blood glucose levels did increase after breastfeeding, but the infant cannot maintain blood glucose levels during fasting. So out of all of the options listed below, I said that the most likely option was option C, which is glycogen storage disease. So this is a defect in glucose 6-phosphorylase, and this enzyme is used in glycogenolysis to convert glucose 6-phosphate to free glucose. So in glycogenolysis, you start out with glycogen, and then an enzyme called glycogen phosphorylase phosphorylates the glycogen and breaks off a glucose and turns it into glucose 6-phosphate. This glucose 6-phosphate needs to be broken down to free glucose. So there's this enzyme in the endoplasmic reticulum called glucose 6-phosphorylase, which dephosphorylates it so that your glucose can be taken up by the blood. So this disease is a defect in this enzyme that dephosphorylates the glucose 6-phosphate. So a deficiency in this enzyme would cause low blood glucose, and that explains the hypoglycemia that the patient is experiencing. This would also mean that there would be a buildup of glucose 6-phosphate if it can't be dephosphorylated, and that would in turn cause a buildup of glycogen in the liver, which would explain the patient's enlarged liver. Glucose 6-phosphorylase is not found in the muscles. So when this process occurs in the muscles, a process called the Cori cycle actually occurs. And that is where glucose 6-phosphate is converted to pyruvate and then to lactic acid. And this lactic acid is then shuttled to the liver to be dephosphorylated. So basically the lactic acid in a reverse reaction is converted to pyruvate and then glucose 6-phosphate, and then this glucose 6-phosphorylase dephosphorylates it so that the glucose can go to the bloodstream. So when you have a deficiency in this enzyme, in this case, it would mean a buildup of lactic acid. So that would explain the patient's symptom of lactic acidosis. One thing that the case study noted towards the end was that the infant was able to bring up glucose levels after being fed, but was not able to maintain these glucose levels. So this enzyme does not have anything to do with the processing of dietary glucose levels, but instead it affects the breakdown of stored glucose in the form of glycogen, which explains that the blood glucose levels were not maintained because the infant was not able to get this free glucose from the stored glycogen levels during fasting. So just to talk about why the other options were incorrect. Option A was a hereditary fructose intolerance, which is also known as an aldolase B deficiency. Aldolase B plays a role in the breakdown of fructose by dephosphorylating fructose 1 phosphate to DHAP. So, a deficiency in this enzyme would cause a lack of free phosphate, and if you don't have free phosphate, then it would affect glycogenolysis. So, back to the enzyme glycogen phosphorylase that phosphorylates the glycogen and creates glycogen 6 phosphate. If you don't have free phosphate to phosphorylate this, then you can't make glucose 6 phosphate. So that would lead to the liver not being able to create this glucose 6 phosphate, and that would lead to a buildup of glycogen in the liver, which would explain the enlarged liver. So this option seemed like kind of enticing at first, but then you go to the next symptom of lactic acidosis, and I realized that without the glucose 6 phosphate, the Cori cycle can't occur and lactic acid would not be created. So that would mean that the symptom of lactic acidosis would be unexplained. Option B was galactosemia, which is kind of similar to option A. It's a deficiency, though, in galactose 1 phosphate uridyl transferase. And this enzyme dephosphorylates galactose 1 phosphate to UDP galactose. So similarly to option A, you wouldn't have any free phosphate, which would create an issue in glycogenolysis, which would mean that glucose 6 phosphate could not be created. It could also cause an enlarged liver because of the buildup of glycogen, but the symptom of lactic acidosis would not be explained because glucose 6 phosphate could not be created. Option D was a glucose 6 phosphate dehydrogenase enzyme deficiency. Glucose 6 phosphate dehydrogenase helps in the early steps of the pentose phosphate pathway. A deficiency in this enzyme would cause a breakdown of red blood cells, and this breakdown of red blood cells would lead to anemia, increased risk of infection, and sensitivity to foods, but it does not explain any of these patients' symptoms. So a combination of the first slide talking about why this condition makes sense for this case, combined with the explanation of why all of these other ones do not make sense, are why I thought that it was glycogen storage disease. And then just to finish up, I have my list of references.